All right, welcome back. We have now a interesting session. They're all interesting, actually, but there's some stuff I'm personally particularly interested in. So first up is DornerWorks, Robbie from DornerWorks talking about the seL4 VMM on the RISC-V Rocket Chip. Please.
Thanks, Gernot. Yeah, that is the rocket chip. Even though it's a satellite, let's ignore that fact. So, like Gernot said, I'm Robbie VanVossen from DornerWorks. I have Michael Doran listed as well. He helped me with the slides and did some work on the project, but he's not here today, so it'll just be me presenting. I want to give a little bit of context about why we did this work. And a little bit of background on DornerWorks if you don't know us, but we collaborate with many customers in different industries to utilize seL4 on real world applications. So we've done a lot with porting to different platforms with an emphasis on virtualization support on different architectures and different devices and adding features on top of that. And so, going forward along with that is with RISC-V being such an attractive platform for any open source solution, but obviously with seL4 as well. We had an interest with implementing virtualization on these RISC-V platforms as well. It's obviously, as stated, not a perfect approach, but a great way to get a lot of the benefits of seL4 without necessarily needing to write everything from scratch. Obviously, that's not the only option now, as many more OSs are coming about, but virtualization is still a great way to start moving your systems over from monolithic OSs like Linux or RTOSes, where you can start doing things like mixed criticality systems where you can actually have good separation, or doing cyber retrofit. But some of the problems with that right now is, one that we kind of gloss over, my problem two, which is, just knowledge of the seL4 microkernel. And that by not utilizing that, you're starting out by sacrificing strong isolation. So, by getting support out there on RISC-V, it makes it easier for those that are interested in that platform to start having more secure systems. And then the other problem is that RISC-V is lagging behind some other platforms for virtualization support. Obviously, RISC-V is just less mature, but it does now have hardware support for virtualization, and software is catching up to implement that. So a little background on RISC-V. It's an open ISA based on RISC architecture. It was developed by Berkeley in 2010, but now the standard is managed by RISC-V International. And a lot of the functionality is expanded with extension modules, and so you can kind of mix and match the implementers can on kind of what functionality that their specific implementation provides. So some examples of that are like the M module, which provides some of the most basic functionality of multiplication and division. You can see a few of the top ones are the most basic ones that you're going to expect a lot of the chips to have. So they also have this G1, which is just shorthand for that, because you do kind of end up with looking at, okay, what does this implementation provide? And you see an alphabet soup of a ton of letters after its architecture size. So they're trying to reduce some of that, but it does make it a pretty interesting model. And then kind of what that also means is it makes it easier for these implementers to create things like custom modules and extensions that they can apply that can fit better in certain domains in niche areas. So things like high assurance security and high reliability, you could start seeing some, I think there was a talk last year about kind of some modifications to a RISC-V ISA just to improve side channel attacks, right? So things of that nature. So obviously that makes it a great fit for seL4, where you have this open hardware and software stack that you can build upon. And then the privilege model, that's important when we're considering virtualization. And looking at the normal privilege model, it's mostly what you would expect. You know, you have machine mode, which is the highest privilege, then it goes up to supervisor and then into user mode. Machine mode, you're usually running, the standard would be machine mode, you're running like your bootloader. The common one now is OpenSBI. And then on supervisor, that's where you're running your OS, and then user mode is where you're running all your applications. With the H extension, the hypervisor extension, it splits both the supervisor mode and the user mode into different versions. So the supervisor mode becomes the hypervisor supervisor mode and the virtual supervisor mode. And then user mode becomes virtual user mode and regular user mode. So the virtual ones, that's where you're going to be running your guest operating systems and their applications into the virtual user mode. And then the hypervisor supervisor mode, that's where you'd be running your hypervisor, and then user mode, regular user mode is where you could then be running VMMs, where you're running other components in the system that don't need to be virtualized but are application. So this hypervisor ISA was ratified December 2021, so it's almost 2 years ago now. And it had a number of updates. One of the most obvious ones, the ones I already went over, is the updated privilege modes. You can kind of see what I was already talking about, although you know, one big difference is the fact of adding a two-stage address translation to help enable that. And so you can kind of see that's one of the most obvious differences between the virtualized user and supervisor mode versus the other ones, is that the two-stage translation is enabled. Besides that, it added things like hypervisor instructions. It added new hypervisor and virtualized versions of registers where you needed more specific things for those configurations. And then it also updated the traps, which is what you would expect, as you need new exception handlers for coming in and out of the virtualized environment into the hypervisor. So previous work on the seL4 VMM, we pitched this to our customer probably like, they accepted it, and then a year and a half later, the contract started. So at the time when we pitched it, no one had done any work in this area. And then we had planned to do everything from scratch. And then once we got on contract, we took a look again, and Yan had done everything on QEMU. So we wanted to figure out what's the next thing that we can do to build upon the awesome work that Yan already did, where he got an initial seL4 VMM working on the QEMU model, which had hypervisor extensions implemented. So you know, we brainstormed some ideas, and we felt kind of the best route forward was to create a soft core implementation that implemented the hypervisor extensions and port Yan's work over onto that. But thanks, Yan. That was very helpful. So Rocket Chip, that is the soft core that we decided to go with. A little bit of background on that. It was also created by Berkeley. This was in 2016. And essentially what Rocket Chip is it's more of an SoC design generator. It emits synthesizable RTL, which means you can import that into different tools that allow you to integrate it on an FPGA and hook it up to other things, whether that's real life SoCs that are on the same board, or whether that is through other PL devices that you want to instantiate on that FPGA fabric. So it does a number of different options. We didn't play around with a ton of different other configurations, because we mostly just wanted to get something simple that worked. But we ended up with like, a 4-core system that we didn't use any of besides the 1 core, and used the in-order core generator, the Rocket one. And obviously there are other options. There are other RISC-V generators out there, other soft cores that are available. We actually went with Rocket Chip because we had done some exploration with seL4 on that already. We had gotten one without the hypervisor extensions running on a ZCU102 in the past, and got seL4 and seL4 test running on that. So we already knew we had a leg up on that platform in terms of just getting base seL4 running. And then we also had the benefit of, with a little bit of research, seeing that someone else had actually already figured out a way to add the hypervisor extension implementation onto that. So for our implementation, that fork that we found, it was done for the FPGA on a Xilinx ZCU104. They do use basically the same, they use the same FPGA on there, but then there's some differences in the board level, and some small other pieces. So we did find that from a hypervisor, a team who's from a hypervisor called the BAO hypervisor. So we started off of their work, and then we got that to work on the FPGA of a Xilinx ZCU102. And a lot of what that took is just using Xilinx AMD's tools to take our generated Rocket Chip RTL, chuck it into their Vivado tool, and then hook it up to the Rocket Chip SoC for all the pieces that we needed in the system. So that's things like resets, memory, clocks. Then we were interested in passing through the UART device for the VM to use. So that's actually what's implemented on the SoC, like the A53 and R5 side. So you can configure through the FPGA fabric to basically give access to the Rocket Chip for that. And then after all that configuration, we did some testing, just some basic testing, built the bitstream, booted it on our board, and then we were able to test with native Linux and seL4 test again. And then just kind of a diagram of what I was describing. You can kind of see on there, it's a little hard to read, but this is the actual SoC chip. So you can kind of see some pieces like the UART IRQs, those get routed through over into the Rocket Chip. And then there's a couple of AXI interconnects. One is for the RAM, and then the other one is for MMIO devices. And so there's like another window you go into in those to kind of specify exactly, which address ranges, how much memory are they getting through those interconnects, and what's actually managed through that bus. And then other than that, it's mostly resets, clocks, and all that stuff wired in. And then our development journey. We found it helpful to kind of describe out what the architecture looks like based on those privilege modes, and kind of just show like what are all our interfaces and what's running where. So obviously you have the PL on the ZCU102 at the bottom is the hardware, and that's where the Rocket Chip is running. And then in the machine mode, we have OpenSBI firmware, like I was saying. So that's your most privileged thing running. It's mostly a bootloader, but it does provide some features that you call into that can do some certain things like cache management and things like that. But for the VMM side of things, we just emulate that. So for the hypervisor mode, what we're running in there is just the seL4 microkernel. And then in user mode, we finish up basically what becomes the whole hypervisor, which is the VMM application. That's also where we have implementations like the interrupt controller, the virtualized interrupt controller implemented, where we do trap and emulate of that, and where the actual seL4 syscalls happen. And then the guest OS is running in the virtualized supervisor mode, and its apps are running in the virtualized user mode. So we ran into two major issues with this port, and actually neither of them were especially hard to solve, but they were quite hard to figure out that they were the problems, which is, classic engineering. So probably the biggest issue was that QEMU did not implement compressed mode, which allows you, it's basically ARM's thumb mode. It allows you to do a mix of either 32-bit instructions or 16-bit instructions. And so in the original implementation, it was assumed that all instructions were 32-bit. Now what that means is the emulation code or virtualization code of the interrupt controller, or the PLIC, it worked on QEMU because the C mode wasn't enabled, and that was where we were emulating some of those instructions, where it was trying to write something, and the way that virtualization layer worked is that we were able to, there was a number of them that we were just able to just say, okay, it wants to write to this range, we can do that. But it wasn't working because some of the instructions were 16-bit now, because our Linux kernel and our Rocket Chip implementation allowed the compressed mode. I think we could have rebuilt our Linux kernel to not use compressed mode, but once we figured it out and realized it wouldn't be that hard to fix, we just made the update for the virtualization code, because now you can support more configurations. It's just a better approach. And then the other piece of that, to fix that, we had to update the check of the size of each store and load instruction to emulate it accordingly. And then there was a number of areas where you have program counter advancing logic. And so that was just hard coded to advance 4 bytes, but obviously it needed to be dependent on, the actual size of the instruction. Then our next major issue was that there is a errata in the QEMU implementation of the interrupt controller, the PLIC. So it basically wasn't correctly handling how you ACK it and re-enable the interrupt. And so basically there was workaround code in for the errata that took us quite a bit to discover. And once we did, it was basically just re-implementing it the way it was supposed to, and then adding in some if-defs around with the QEMU implementation for the time being while that errata still exists. So we set it up so both platforms were still functional. And then besides that, there was mostly just minor issues. Obviously, we had a new DTS that's specific to the Rocket Chip on ZC102, so that needed to be included. It's worth noting that it needs to be updated more often than you would expect for most other platforms, or at least just as much as the ZC102 is today if you utilize PL devices, or if you are going to be adding more PS devices in. You could kind of throw a bunch of them in and just set them to disabled or whatever, but for the time being, we left it really simple, and we were just like, here's the definition of the Rocket Chip, and here's the UART that's hooked up to you. Other than that, we had to update our memory configuration. Our RAM disk and kernel was quite a bit bigger than the QEMU image, so we had to increase our allocator pool. OpenSBI also includes kind of like a serial API, but we thought it was more interesting to pass through the UART, and so we took that approach instead. and updated our kernel configuration accordingly for that. And then since we were also actually using a newer Linux kernel than what Yan used, so there was an update to the OpenSBI spec that the newer Linux kernel expected. So we had to implement a new SBI, we had to virtualize a new OpenSBI call. And so the results for us is that we were able to get a single Linux VM booting on the Rocket Chip with that UART pass-through. So that's that one VM booting. And also, as a result, we open sourced and mainlined this work. Currently, there is a issue open. There is a bug with the build. I have some PRs up. And, one's merged, one still needs review. I think once that gets through, that kind of solves the issue. And then besides that, we also included a bit of documentation update. So we added the Rocket Chip on ZC102 with hypervisor extensions as a supported platform. So if you go look at it, you can actually see two. They look almost exactly the same, except one has VMM support, and then it goes to a different page with different instructions. And we also provide documentation to replicate our results, as well as we have some pre-built bit stream for that implementation on the ZC102. So if you have a ZC102, you should be able to follow the instructions on that link, which points to a repo of ours, which has some scripts and that bit stream, and be able to essentially replicate what we've done. And next steps, I think, is mostly to try to match the feature set of what the VMM can do on other architectures. So first step for that, or at least one of the parallel steps that could happen, is supporting more advanced configurations. Just a single VM with a UART isn't very exciting. So, other configurations that we'd want to be able to test and support would be multiple VMs. We'd want serial server, we'd want VirtIO devices, we want more pass-through devices, especially ones that use DMA to make sure that those function correctly. And, if possible, multi-core. And then another piece we would like to do is run on real hardware. Obviously, that's still just not possible. We're waiting for real hardware to be that we can buy that will have the hypervisor extensions. Hopefully that's sometime soon. And then other than that, I think kind of the biggest remaining thing is using one or more of the standardized VMM implementations. So the most obvious one right now is the CamKeys VM, and being able to support that. MicroKit VMM, like Ivan was saying, that he's got some in-progress work for the MicroKit VMM to run on RISC-V, so it would be natural for him to get that working on QEMU, and that might be an area where we could port that onto Rocket Chip again, right? Really the kind of approach that was taken for the VMM was a lot of the code was ripped out from the various library repos that could be reused, and then new functions created. So it's kind of just like one big file. And so that kind of would, one of the steps also is to get that stuff mainlined into the libraries. So kind of reversing that and making sure we have all the new architecture RISC-V specific code upstreamed in the correct locations. And that would support running on CamKeys VM. And that's all.
Thank you.
So you mentioned like upstreaming the work that you've done, but to my knowledge, like the RISC-V hypervisor changes to seL4 itself, which are pretty big, haven't been. Do you have any plans to do that?
That's a good question. We would definitely be interested in doing it it's probably lower priority than some of our other PRs that we currently already have open. But yes, I would like to.
Hey, hi. So you mentioned the RISC-V is lagging in the machine learning feature in terms of hardware. Can you elaborate that one? For example, you mentioned about device pass-through. So does RISC-V have something like a SMB in ARM?
So I guess mostly what I meant was just that it's just newer. It has most, if not all, the features we need, but like what I mean is, no one has silicon out that you can purchase that has it on it, right? So it hasn't been used very much. It's mostly only been used in the context of QEMU, been used in the context of the rocket chip, right? So it just needs to be used more. It needs to be put on real silicon so that we can actually throw it on a board and use it, right? I don't know off the top of my head. I think they have some IOMMU spec or they're working on it, but I don't know that for sure. I'm sure someone in the room knows better than me on that.
Yeah, I have a quick question. How many bugs did you find?
How many bugs? Yeah. It actually, it wasn't that many. Yeah, it was really just the changes I listed. Honestly, I was pretty surprised, that porting to a new platform, even with it only ever being tested on QEMU, was relatively simple. I mean, I called them major issues, and like I said, they were a little tough to find, but they were pretty easy to fix. So. I think RISC-V's model for virtualization is pretty nice, and it shouldn't be hard to adapt to new platforms as they get released.
I'll channel Lucy. Have you looked at performance?
Oh, not at all. But the Rocket Chip, since it's a soft core, is essentially just like the silicon.
Yeah, I was mostly interested in performance of the VMM in particular.
Oh, gotcha. Yeah, no, we haven't done any performance measurements, but I think that would kind of go hand in hand with doing newer configurations and getting things like Vert.io net set up so we can communicate between multiple VMs, and then we can get a few interesting metrics that our customers are usually interested in.
Seems no more questions. We're actually slightly ahead of time. Last chance? No? All right. Then thank you very much.
All right. Thank you.